Welcome to the second lecture in a series on industrial electricity. Today we're going to talk about Ohm's law and power. Then we're going to talk about efficiency, especially as it relates to motors, such as this 30 horsepower, 440 volt AC motor that was used as a winch off a ship. We start with a review of scientific versus engineering notation. We'll start with an example. Suppose you had 1.23 times 10 to the fifth power, and that was a number expressed in watts. That would be 123 kilowatts. If you were to write that out, it would be 1, 2, 3, followed by 3 zeros. Let's see if that's correct. So we have the decimal point was originally here. We walk it over 1, 2, 3, 4, 5 places. Here, we would have said kilo. You remember the prefixes? Kilo is 10 to the third, so you could rewrite this as 123 times 10 to the third watts, or 123, 0, 0, 0. Your calculator could be useful to you for this. You could enter 1.23, and then this button down here, this x, 10 to the x, so you push that, and then enter 5. And there you see it's 1.23 times 10 raised to the fifth power. You hit equals. There it is. And you remember this engineering button. If you push that, whoops, we're in the wrong mode. Go back to normal mode. Let's try that again. So 1, 2, 3 to the fifth power. Whoops, sorry. 1.23 raised to the fifth power. There it is. And then hit the engineering button. And there we go, 123 times 10 to the third. Remember, in scientific notation, this first digit was between 1 and 9, whereas this first digit in engineering notation is 1 to 999. And here, this exponent is a multiple of 3 where there were prefixes such as tera, giga, mega, kilo, the unit, then milli, micro, nano, and pico. And all of those should already be on your note card. That's something you want to commit to memory, as we're going to use that again and again in this course. From Chapter 2, we talked about a closed loop. We talked about polarity, voltage, current, and resistance. We said that there was a relationship between these three. And that relationship was Ohm's law. We had a device to help us remember these. So we would put them in a wheel like so. And then we use what we called the cover-up method. So if you wanted to figure out what the voltage is, you'd cover up the voltage. You'd say a voltage is a current times a resistance. So E is equal to IR. A current, we cover that up. That's a voltage divided by a resistance. And the resistance is a voltage divided by a current. I believe I mentioned that voltage, sometimes you'll see that as E for electromotive force, and other times you'll see that as voltage. There's a linear relationship between these three as described by Ohm's law. On this axis we have voltage. On this, we have current. For any given resistor, there will be a line where we could figure out a voltage relationship to a current relationship. This line would be said to have a low resistance. This one would have a high resistance. And then if we looked at the extremes, This one here, when you're completely vertical, this would be a short circuit. That's a short circuit hid behind me. And the other one, the other extreme, is this one, where we're on the horizontal. And we would call that an open circuit. In a short circuit, the current is infinitely high, but there's no voltage. In an open circuit, the voltage can be very high, but there's no current. We talked about schematic diagrams. On that schematic, you may have seen a voltage source, a cell, not to be confused with a battery. This is an example of a cell. Here we have a single 1.5 volt cell. A battery would be composed of multiple cells. This battery, a 9 volt battery, so 9 volts is actually 6 times 1.5 volts. And if you were to take this apart, you would be able to see the individual cells inside that battery. This symbol is for an AC voltage source. Here's a meter. You may have seen one of these, certainly in the lab. So they typically have a dial. On that dial, you'll have several different positions. One for ohms, and that would be the omega symbol. DC, which is typically 2 bars, and then AC, which is a sinusoid. And that is a digital multimeter. Here's an ammeter, a voltmeter, and a switch. We put all those together to make a complete circuit, such as this. Here we have a source, the switch, we'll put the ammeter there, a resistive load, and then a voltmeter. You'll notice that the current is flowing through the ammeter and then flowing through the resistor, then returning back to the source. There is a tiny amount of current that flows through the voltmeter, but it's not enough to concern ourselves with in most circumstances. You'll often hear me say that it's current through the ammeter, and we measure voltage across a particular element. In this case, we're measuring the voltage across resistor R1. Of course, we use Ohm's law to determine the relationship between the source voltage, the current, and the resistance. There are 3 different problems you'll encounter with Ohm's law, and I'll show you each one of them here. So this one, we have the source voltage, and we know the resistance. We're asked to find the current. Here, we know the voltage, we know the current, and we're asked to find resistance. Next, we know the resistance and the current as, let's see, what did we write this as 10 amps. You're asked to find the source voltage. So I is equal to E over R. R is equal to E over I. And these are all coming from our cover-up method. So R is E divided by I. And finally, E is IR. Plugging in the variables. 5/2, so the current in that particular circuit is 2.5 amps. Here, it's 10 volts over 5 amps. So the resistance is 2 ohms for that circuit. Here, the voltage is 10 times 2, so the voltage is 20 volts. It's Ohm's law. You have 3 variables, you're given 2, and you'll be asked to find the third. At this point, we transition into Chapter 3, where we talk about power, energy, and efficiency. We mentioned a power supply and a resistor. And the purpose of that resistor is to convert electrical energy into heat. You'll remember that from the first lab we did, where the 1-watt resistors that were plugged into the power supply got fairly warm. There's something you should know about resistors, and that is the fact that they are everywhere. We can't get rid of them. For instance, this wire, that wire acts as a resistor. The motor is a good example. We have a power supply, and then we have resistors. We have resistors from the wires connecting the motor. We also have the resistance of the wires inside of the motor. And those wires get hot. There's no avoiding it. There's going to be power lost in the form of heat from this system. This is the output shaft of the motor. This is the power supply. And this heat, or this resistor, represents the heat lost by the motor. Before exploring efficiency, let's do a quick review. First, Ohm's law. And I know we've been over this a few times, but it's very important, so we'll mention it again. Power, same deal. Again, very important. You need to remember these. We'll put a wheel around them. So Ohm's law. And there's the power law. Using the cover-up method, E equals IR, I equals E divided by R equals E divided by I. Power is equal to IE. I is equal to power divided by voltage, and voltage is equal to power divided by current. I believe we talked about the mathematical manipulation you can do, and you'll end up with power. Let me get that up so you can see it. Power is equal to IE is equal to I squared R is equal to I squared divided by R. These two forms can save you a bit of work. There are 3 types of power problems. You're given a supply, in this case 10 volts, at 2 amps. You're given a supply voltage and a resistance, and you're given a current and a resistance. Oh, this was 2 ohms. You can calculate the power as IE, because you have the voltage and you have the current. So that's 2 times 10. So the power in this circuit is 20 watts. This one here, power is equal to voltage squared divided by resistance, because those are the 2 values you have. So power is equal to 20 squared divided by 2, which gives us 200 watts For this one, power is equal to current squared R. So I squared R. That's 3 squared by 8. So the power is 72 watts. Now you might ask, what does this have to do with a motor? Well, let's find out. So here is our motor. We have a shaft, and we have electrical wires headed to that as well. So we talk about, so for this motor, we talk about mechanical power. And we talk about electrical power. There's a few things you need to add to your note card. So I'm going to call this equations. Equations for the note card. And here they are. 1 horsepower is equal to 746 watts. 1 horsepower is equal to foot-pounds of torque multiplied by the RPMs divided by 52. So this is the torque, and this is the speed at which the shaft is turning. Here's a few more. I'll explain this in a minute. One more, and that is efficiency. And that tells us that power out is equal to power in. By the way, this symbol here is the Greek symbol eta. It looks like an N, but it's got a slightly longer tail. Okay, let's see how we can use these equations. So here's an example. Find the torque for a 5 horsepower motor that has a speed of 3,550 RPM. So 5 is equal to the torque, that's in foot-pounds, by 3,550 over 52. So go into our calculator. We'd say 5 times 52 divided by 3,550 gives us about 7.4 foot-pounds of torque. All right, so there's one equation. So let's continue. Let's keep with our 5 horsepower motor, and let's convert that into kilowatts. So we're taking mechanical horsepower and we're converting it into kilowatts. So that one's right here. So we would say 5 horsepower. Then we're going to use dimensional analysis where there are 746 watts per 1 horsepower. And you multiply that and you'll end up with 3.73 kW. Again, dimensional analysis, the units cancel out. So we start out with 5 horsepower, we multiplied by 1, which is essentially what this ratio is, and we arrived at 3.7 kW. Right, that wasn't so bad. So let's continue on. We'll do another example. So calculate electrical power for a 75 horsepower motor. We use dimensional analysis again, so 75 horsepower, 746 watts over 1 horsepower. gives us about 56 kW. And if you were to represent that, you would say there's the electrical side, and here is the motor. We're drawing these as simple DC motors here. There's a division. We call this the electrical side, and we call this the mechanical side. Over here, we talked about 75 horsepower from the shaft, and here we mentioned that it was 56 kW. There's only one problem with this, and that is there is no such motor in all of the world that will do this, because we've forgotten something. We've forgotten our wires, haven't we? I mean, way up here we talked about resistors giving off heat, right? You give off heat. And we've got to account for that in our motors. And that's where this equation comes to play, where we talk about efficiency being the power out divided by the power in. And we know that our motor has mechanical power out, and it has electrical power in. Those are different, but we do have an equation that helps us with that. So here's our way of converting mechanical to electrical power. All right. Here we should make a statement here. In the real world, no motor is 100% efficient. It doesn't exist. No such thing. Because in the real world, we have power coming in. So we describe this as power going in, and this is power going out. And then we have this, which is power lost. And that's unavoidable. By the way, this is called a power flow diagram. And it helps us calculate efficiency. So eta is equal to power out over power in. Another way of saying that is this is power out over power out plus power lost. Because power in is the power lost plus the power out. For our example, let that motor, so we got this 75 horsepower motor, let efficiency equal 92%. So from before, we described power out is equal to 75 horsepower. Using dimensional analysis, we converted that to watts, and we said that's approximately 56 kW. Now we can use our equation here, where we say 0.92, because it's 92% efficient, is equal to the power out, which is 56 kW, over power in. Solving for that, the power in is approximately 61 kW. If we were to plot that in a power flow diagram, it would look like this. Where we have 61 kW electrical going in, we have 56 kW going out, and we lost 5 kW along the way. Efficiency is equal to 92%. That's what that looks like. 92% of the power made it from in to out, and the 8% was lost. Just for reference, 5 kilowatts is a fair amount of power. That is equivalent to 5 space heaters that you might have in your house. Another way of viewing this is we have our power supply. We have the resistors. Ideally, we wouldn't have any, but we do. And then the shaft for the motor output. We have 56 kW coming out, which is equivalent, again, 75 horsepower. We have 61 kW supplied by the power supply, and the resistor is giving off 5 kW. Again, that resistor just represents the wires that are wound inside the motor, and a few other losses that we might talk about another day. While we're on this subject, let's talk about how we pay for electricity. So energy is equal to power by time. So how much, how fast, because power is a rate, and then the time is for how long. By the way, energy has a bunch of different units that we could use. We could talk about the horsepower hour. We could talk about BTUs, talk about calories, we could talk about the joule. For this course, we're going to stick with horsepower hours and kilowatt hours. Okay, those are the two that we're going to be using. Here's an example. Suppose we are paying 5 cents per kilowatt hour, which is pretty good. That might be for an industrial setting. We want to find the cost to run that 75 horsepower, 92% efficient motor for 1 month. Let's see how we would do that. Energy is equal to power by time. Our power, let's see, we did that already, didn't we? We go back up here. So it's 61 kilowatts. That's on the electrical side, right? We need 61 kilowatts to make 56 kilowatts on the output. So this is 61 kW multiplied by, what do we say, 1 month? So we'll call that 24 hours by 30 days. So that equals, let's get the calculator going here. So 61 E3 times 24 times 30. I'll put that back into engineering. So that's, what do we got there? So that's about 44 million watt hours. It's quite a bit of energy. While this is technically correct, I'm going to convert it over to kilowatt hours just so it works out better for our calculations. So that's 44,000 kilowatt hours. All right, now we take that number, so 44,000 kilowatt hours. We use dimensional analysis where we say electricity cost 5 cents per kilowatt hour. We cross off the units. So the cost to run this motor, 44,000 times 0.05. There we go. So the cost to run this motor is $2,200. So every month, if you're going to run a 75 horsepower motor, that's what it's going to cost you. All right. Well, that's enough for today. Let's do a quick review and pull the highlights out of this lecture. Okay. This was an Ohm's law review, and we saw that there were 3 different ways that we might encounter these problems. Given 2 variables, we'll be asked to solve for the 3rd. This was a power review. Again, power had 3 variables, just like Ohm's law did. And given 2, you'll be asked to find the third. Those are the 3 different ways that that could be expressed. We mentioned the motor. We talked about electrical power and mechanical power. We had some conversion tools that we could use. So 1 horsepower, 746 watts. Oh dear. This here should be horsepower. Why didn't you catch that earlier? Horsepower is equal to torque by speed divided by 5252, where torque is in foot-pounds and the speed is given in revolutions per minute. Then we had this discussion about efficiency. Eta, which is our symbol there. Efficiency is power out divided by power in. I should note that this is never going to be greater than 1, right? Efficiency will always be less than 100%. Don't believe anybody that tells you otherwise. This was an example. We were given a 5 horsepower motor. We were given the speed, and we were asked to solve for the torque. We were also asked to figure out, given this mechanical power, what is the equivalent of electrical power? For this ideal motor, we determined that 75 horsepower mechanical was equal to 56 kW electrical. But that never happens because no motor in the real world is 100% efficient. We always have power lost. We ran the example again, this time 75 horsepower with an efficiency of 92%, and we determined that we needed 61 kilowatts on the input electrical side to make that happen. And that's shown here again, where the output is 56 kW or 75 horsepower. The final thing we talked about was this very useful equation, which tells us that energy is the product of power and time. And we mentioned that there are units of horsepower hours and kilowatt hours. Those are the ones we'll be using mostly for this course. We concluded by determining the cost to run this 75 horsepower motor that's 92% efficient for 1 month. And that was a multi-step process. First, you had to figure out what the energy was, and once you knew what the energy was, you could calculate how much it cost, because energy is sold by the kilowatt hour. If you have any questions, you can leave them in the comments down below, or you can put the information into our shared class folders. Until next time, be safe out there.